In this video, I will give some hints towards solving a breakthrough problem using real experimental data for bovine serum albumin, BSA. The same column was used as in the video linked up here somewhere. A water solution with pH 8 and a BSA concentration of 3 mg per liter is to be purified using adsorption in an ion exchange column. The column length is 30 millimeters. The column diameter 6.4 millimeters. Void fraction 34%. Dead volume 0.2 milliliters. Flow rate 2 milliliters per minute. The packing material is source 15Q for ion exchange. The particle diameter is 15 micrometers, and UV detectors and conductivity detectors were used. In this breakthrough curve, the dead volume has not been deducted. Task A. Calculate the degree of utilization at 5% breakthrough and how much BSA has been absorbed at that point. B. Calculate the superficial velocity and the real velocity, interstitial velocity, in the column in meters per second. To calculate the degree of utilization, we first need to determine the capacity. Thus, once again, we start by determining T star. We draw a vertical line and compare the area above the breakthrough curve to the right, that is later than our vertical line, with the area below the breakthrough curve to the left of our vertical line. We move the line until we find a spot where these two areas have the same size. Note that we, once again, get a strange area unit, milliabsorbance unit times milliliters, and that we need to translate that to a reasonable unit for column adsorption capacity, that is milligram of BSA. Note also that in this case, you also need to consider the dead volume, so you have to deduct that to get to the adsorption capacity. When you have calculated the capacity, it is time to determine the degree of utilization and hence also how much BSA has been adsorbed at the breakpoint. First, locate the breakpoint in the diagram, that is the point where the breakthrough curve is 5% of the maximum, assuming that absorbance is linear dependent on concentration. A first approximation of the degree of utilization would be to divide the breakpoint TB with T star. But if we do that, we assume that the area below the breakthrough curve up to the breakpoint is negligible. Better would be to actually calculate the area below, that is how much have come out at TB. As before, the easiest way to calculate the area below is likely to draw a triangle that has the same area as the area below the breakthrough curve. Thus, when you draw the triangle, the part of the area below the breakthrough curve that is not inscribed inside the triangle should be of the same size as the part of the triangle that goes outside the area below the breakthrough curve. In this case, the area below the breakthrough curve is rather small in comparison to the area above, but I encourage you to do that calculation anyway and see for yourself how large or small a difference it makes. In subtask B, you should calculate the superficial velocity and the real velocity. The superficial velocity is the velocity the flow seems to have if you think of the column as being empty. The real velocity through the column depends on how tightly packed the column is. This since the flow cannot flow through the particles. It has to flow around. And it's rather common that the interstitial velocity is calculated neglecting tortuosity. But to get to the true actual velocity in the pores between the particles, you have to make an assumption about tortuosity.